So section 19.5 is on the relationship between the concentration of our reactants and the amount of time that has passed since a reaction started. And what we're going to do in this section is learn how to modify the rate law to make it even more useful. The rate law can be modified with some math so that you can calculate the concentration of any reactant at any time. And we're going to go through this modification of the rate laws one at a time for three different orders of reactions. So we're going to start with the first order reaction. We're also going to do a second order reaction and a 0th order reaction. In the first order reaction that we're going to look at, we're going to keep it really simple. One reactant turning into one product. So we've looked at examples of that type of reaction before, like maybe it's a Cl2 molecule turning into 2 chlorine atoms, something like that. And for this really generic first order reaction, the very first thing that we looked at was the average rate, which we said we would calculate by taking the negative change in the concentration of A over the change in time. And we talked about all of where that came from, why there's a negative sign, all that stuff. And then we also talked about the rate law, where rate equals little k, the rate constant, times the concentration of the reactant A. And since we know that this is a first order reaction, we know what the exponent is in this rate law. It's not unknown to us. So what we can do is actually combine these two equations for rate and come up with what we call the integrated first order rate law. The integrated first order rate law is the natural log of the concentration of A, our reactant, at any time. So that little t is representing whatever time that we want. That is equal to negative little k rate constant times the same time that we're talking about, like maybe 120 seconds, plus the natural log of the concentration of our reactant A at time 0, or the very beginning of the reaction. So this notation, A to the 0, or not to the 0, A sub 0 is our initial concentration at time equals 0. So that seems like a pretty big leap there, that we went from those two rate equations to this thing that's got natural logs in it. And how on earth did we come up with this beautiful equation right here? Well, many of you are not going to appreciate the derivation of this equation, but I'm doing it anyways because you know me and I love me some math. This derivation comes from, first of all, combining the two rate laws. So we've got negative delta A over delta T, and that's equal to Ka. And what I'm going to do here is replace the deltas with the lowercase letter d, because I'm getting ready to do some sweet math. And in math, mathematicians use the letter d instead of the delta symbol. So depending on what math class you're in right now, you might be getting pretty excited. or you might be getting kind of maybe a little bit triggered. So the next thing I'm doing is I'm combining like terms. And if you haven't made it to Math 151 yet, you're just along for the ride right now. And then what we're going to do is integrate both sides of this equation. The left side, we are integrating from initial concentration of A to A at any time. And that's going to be the integral of 1 over A dA. And I didn't lose my negative sign. I just want to have it out in front there. And then the right-hand side, we are integrating from time equals 0 to time equals t, dt, and k, because it's a constant, it's going to end up out in the front as well. And oh, isn't this so exciting? So we get the negative natural log of a at time t minus the natural log of a at time 0, and that is equal to kt. And then we just do some algebra to rearrange this last version of the equation. We do some algebra to rearrange it into this really pretty form that I wrote up here in red. So if you have not made it to Math 151 yet, this is where you start listening again. So another version of the integrated first order rate law, if you're doing a reaction with gases, instead of using molarities, we could use the properties of a gas. So we could go pressure over our T for temperature, so that's a capital T, at time T is equal to negative, got to keep our T's straight here, K time T plus the natural log of P over our temperature T at time equals 0. So both of these in red right here, both of these are the integrated first order rate laws. These allow us to calculate the concentration or the pressure, if it's a gas, at any time that we want over the course of a reaction. These integrated rate laws are written specifically in this form right here rather than just like this, kind of the way that they are born from the math. They're written in this form because they take the form of y equals mx plus b, which means that we can actually graph data from these integrated first order rate laws. We can graph our data and get a linear plot of our data. So I'm not really stoked on using the gas version of this because of all the variables that are in there. I don't really want to do that. So I'm going to rewrite the molarity version, natural log of A at time t equals negative kt plus ln A at time 0. And underneath it, I'm going to put y equals mx plus b. So in this equation, in this form, our y is the natural log of A. So that at any given time, at time t. So that's what we're going to be plotting over here, the natural log of A at time, whatever our time is, and we're going to be starting down here at 0. And then our m, the slope, is going to be negative k. And our x is going to be the natural log. Nope, I looked at the wrong thing. X is going to be time, little t. So that's going to be down here. And our intercept is going to be the natural log at time 0. So that means that we'll be crossing our y-axis at time 0. So when we graph our data, we can tell from the negative slope that we're going to get a line like this with a negative slope. And the slope of that line is going to be equal to the value of K. So let's see how we could use this equation. Let's say that we have this reaction 2N2O5, and it is going to 4NO2 plus O2, and we know that it's a first order reaction. In order to use the integrated rate law, you have to know if it's first order or second order or zero order. And for this reaction, we also know that the rate constant, little k, is 5.7 times 10 to the minus 4, and the units are going to be 1 over second, or second to the minus 1. The initial concentration of the N2O5 is 0.53 molar. And our question is, what is the concentration after 150 seconds? So for a problem like this, where they are asking you specifically to calculate the concentration after a particular amount of time has passed, that's your hint that you need to be using the integrated rate law. And since it's telling us that it's a first order reaction, that means we know that we're using the integrated first order rate law. So that's going to take the form, the natural log of N2O5 at time t, that's what we're trying to figure out, is negative kt plus the natural log of the concentration N2O5 initially at the beginning of the reaction. And again, our unknown is the natural log of N2O5 at time t. Our k, the constant, is 5.7 times 10 to the minus 4. Units are second to the negative 1. The time that we're dealing with here is 150 seconds. Typically, you're not going to see incompatibility with the units here, but you should always double check and make sure that they are the same. And then to that, we are going to add the natural log of our concentration at the starting point or at time 0. And so these equations are really easy to use because we are literally just plugging stuff in and solving. 5.7 times 10 to the minus 4 times 150, and that's negative. And then to that, we are going to add the natural log of 0.53. And we get a concentration, a natural log of N2O5 at time t. Our value is negative 0.720. And now you have to be comfortable with undoing that natural log. N2O5 at our time t is e to the negative 0.720. So e to the is the function that is undoing that natural log, and we get a concentration of 0.49 molar.